Welcome all to this week's GOAT seminar. And today we have Vít Jelínek as a speaker, and he will be talking about Fishburn numbers.
Thank you. Thank you for inviting me to this seminar. Thank you for coming to hear my talk. I will talk about Fishburn numbers. And I should start by pointing out that this is not really a computer science talk. This is more a combinatorial talk. And also, this is not a talk which is geared towards presenting one big result, but it's mostly a sort of overview of the topic. And I will begin by explaining what Fishburn numbers are. I don't expect many of you have met them before. I will say something about the asymptotics and congruence properties of those numbers. And finally, and this might be the longest part of the talk, I will be speaking about the connection between Fishburn numbers and their combinatorics and Catalan numbers and their combinatorics. So let me begin with the definitions. And the main definition here is the definition of an interval order. An interval order that's a partially ordered set, say P with some order relation, which has the property that I can assign to every element of the poset an interval, say an element X, is assigned an interval Ix such that X is strictly smaller than Y if and only if the maximum of the interval of X is strictly smaller than the minimum of the interval of Y. So the interval of X is completely to the left of the interval of Y. And if the poset can be represented by intervals in this fashion, I will say that it's an interval order, and the collection of intervals is then an interval representation of the poset. So down here, you have an example of an interval order, a Hasse diagram, and here's a possible interval representation. Say this minimum element received interval 1, 2, which is completely to the left from the intervals 3, 3. So these two elements are comparable and so on. Not every poset is an interval order. Here's a picture of a poset that isn't. This is the so-called 2+2 poset consisting of two disjoint chains of length 2. And I mean, you can easily convince yourself that there is no way to assign intervals to these four elements to make it an interval order. And in fact, this is the unique minimal poset, which is not an interval order. Fishburn himself has proven that a poset is an interval order if and only if it does not contain, if it avoids 2+2 as an induced subposet. And that brings me to Fishburn numbers. And Fishburn numbers, that's a sequence of numbers which count these interval orders. So f of n is the number of unlabeled interval orders with n elements. Unlabeled means that I'm really counting isomorphism times. And I'm starting with the index 0. So this is f0, f1, f2, f3, and so on. So for instance, f3 is 5, meaning there are 5 possible interval orders on 3 elements. Like this. 1, 2, 3, 4, 5. Yes. And so on. So Fishburn has defined these numbers and asked some questions like, is there a formula for those numbers? Is there something to say about the asymptotic growth and so on? And it turned out that those were at the time quite challenging questions. But what helps is that these Fishburn numbers are not just counting interval orders, they are also counting some other related objects. And the first such family of related objects has been introduced by Fishburn already, and those are the so-called Fishburn matrices. Fishburn matrix is a square matrix of non-negative integers, which is upper triangular, and every row and every column has a non-zero entry. And whenever I'm talking about Fishburn matrices, the key parameter that I'm interested in is the so-called weight, which is the sum of its entries. Down here you see the 5 Fishburn matrices with weight 3. And it turns out that these matrices are in bijection with interval orders. I will sketch how this works in a moment. And in particular, the number of Fishburn matrices of weight n is exactly the nth Fishburn number. Here's the idea how a matrix encodes an interval order. So you start with a Fishburn matrix, and every entry in that matrix, such as this entry in row 1 and column 2, encodes some number of intervals. So this is row 1 and column 2, so this entry is encoding intervals from 1 to 2, and this number 3 tells me that I want to have 3 copies of such intervals. So in this way, all the entries in the matrix give me a collection of intervals, and from a collection of intervals, I can build the corresponding interval order, where every element corresponds to one of the intervals, and the ordering relation is what I defined before. Right. Is everything clear so far? Good. Right. And so this was in the 1970s, and then for a few decades, nobody really cared all that much. But then, after a few decades, people started stumbling upon other combinatorial objects, which also ended up being counted by Fishburn numbers. I will not give you all the definitions. I'll just mention the names. SN sequences, Stoimanov matchings related to some invariance in a knot theory, several classes of pattern avoiding permutations, and so on. So this is how people became interested in those Fishburn numbers. And what did they discover? Now, first of all, in 2001, Zagier found a rather elegant formula for the generating function of those numbers. What you see here, it can be deduced by like a direct combinatorial argument, which is direct but not really short. So I will not tell you how it is done unless somebody asks me in the end. What is much more sophisticated, and what was really the main result of Zagier, is that starting from this formula, he could deduce a quite precise asymptotic for the Fishburn numbers, which is the formula you see here. In fact, Zagier could make it even more precise by expanding this stuff that I have hidden in the big O of 1 over n term. And the arguments used to derive this asymptotic were quite involved and quite tricky, and used rather advanced tools from analytic number theory. And already the name of the paper where all this appears is Vasiliev invariance and a strange identity related to the Dedekind eta function should somehow give you a feeling that this is not really an elementary proof. And I will not be showing you this proof either. Instead, I will show you something else. I will show you the heuristic numerical argument that Zagier used to deduce this formula non-rigorously before he was able to prove that the formula actually holds. And it's remarkable that Zagier actually gives this heuristic, totally non-rigorous argument in the paper side by side with this sophisticated, complicated proof. And I think this is somewhat a useful skill to have. So I'll go through this this numerical reasoning. Okay, so I'd like to know how large the Fishburn numbers are, how fast they grow. And I have a fairly explicit formula for the generating function, and I can feed this formula to some symbolic algebra software, and it will be able to compute with no problem, let's say the first 1000 coefficient in that formula, or maybe even 2000 if I'm willing to wait for a while. So now I'm given a file which is like several megabytes, which contains the first, say, 1000 Fishburn numbers. And I can like eyeball these numbers and take a guess that they seem to behave like some exponential times n factorial. That's not such a wild guess to make. And now I would like to estimate numerically what this constant c should be. Well, it should be 6 over pi squared, but that's not something you can like eyeball from the data directly. So I first transform this sequence of quickly growing numbers into a sequence of numbers that do not grow nor decrease. So I take this ratio of fn plus 1 divided by n times fn. And if indeed the numbers satisfy this kind of asymptotic, then this sequence of ratios should approach to the constant I'm after. So I compute these ratios, and now I have 1000 numbers, and indeed I'm happy because they seem to be approaching some non-zero constant. But they are rather slow in approaching that constant. So at index 1000, I get something like 0.608236163, which doesn't remind me of any famous number that I know, and it certainly doesn't remind me of 6 over pi squared, which is something different. So with my hard work of computing 1000 coefficients, I only basically get 2 digits correct or something like that. So that's not enough to guess what the limit should be. So what can I do? I can transform this sequence of numbers to a sequence which approaches the same limit, but faster. And a trick to do it is to use the so-called difference of a sequence, which is just another sequence whose terms are differences of adjacent terms of the original sequence. So that's what I would denote delta of an. And the key property of this difference operator is that if I apply it to a polynomial, or let's say if I apply it to a sequence that behaves like n to the d, I obtain a polynomial 1 degree lower, and plus terms of even smaller degree. And that's also true if the degree is negative. It's not true if the degree is 0, in which case I have a constant sequence, say constant 1 in this case, and the difference of a constant sequence is the 0 sequence. And now to actually use this for my sequence Rn, which is what I'm interested in, I take a guess or a hope that maybe, if I'm lucky enough, the sequence that I'm interested in will behave as the constant, which is the limit I'm interested in, plus the error, and the error, if I'm lucky, might behave like some kind of Taylor expansion into powers of 1 over n. I mean, not every sequence which approaches the limit c will have this particular form, but it's a reasonably general form so that I may hope that my sequence will have this form. And then with this hope, what I can do is first multiply my sequence Rn by n. Now I have a sequence where the dominant term is linear with the constant c and then terms of lower degree, and apply difference to this new sequence. So first I increase the degrees by multiplying everything by n, and then I decrease them by taking the difference operator, and I end up with a sequence where the beginning is well, differentiated into c. This constant term here is destroyed by the difference operator, and what remains are terms of order 1 over n squared. So this numerical manipulation, if everything works as I imagine it to work, gave me a sequence which has the same limit as before, but now the error term is of smaller order. And I can iterate this, say I pick some number k, and I take my sequence, multiply it by n to the power of k, divide by k factorial, apply difference k times, and believe that I have a sequence which goes to the same limit, but with even smaller error term. And of course, this is like an experimental trickery. If I choose k to be too small, then this error will be too large. If I choose k to be too large, then since I'm only operating on the first 1000 terms, then I might end up with complete garbage. But if I choose k to be 100 and do this trick, then I end up with a sequence whose final term differs from 6 over pi square by something tiny. So I get some, say, 180 digits correct. And this should convince any normal person that 6 over pi square is indeed the correct limit. And of course, apart from normal people, there will always be mathematicians who will just say, and so what, this is not rigorous, I want to see the proof. And well, those people can read Zagier's paper with the proof. I also remark, and that's something that Zagier does not mention, probably because it's well known, that if you have this numerical approximation, so this kind of mysterious real number, and you wonder what might be the formula for the real number, well, there are tools for answering exactly those questions. There's like, for instance, there's some online inverse symbolic calculator, there's a computer program like this, and many others possibly. So this is how Zagier figured out what the correct asymptotic of Fishburn numbers is before he could prove it. And another interesting aspect of Fishburn numbers that I'd like to mention is there congruence properties. So up here, what you see are the first 100 Fishburn numbers taken modulo 5. Notice anything interesting about this sequence of numbers? There are many zeros, and in fact, there are zeros which appear periodically. So every value of index 5k plus 3 or 5k plus 4 is 0, and then there's another sort of regularity appearing on values 5k plus 2 and 5k plus 1. And something quite similar appears also if you take Fishburn numbers modulo 7. Again, there will be some zeros appearing periodically, and again, there will be some congruence relations between terms where the congruences depend on the index modulo 7. And something similar also happens for other primes, not all primes. For instance, there's nothing interesting that people could spot when you take Fishburn numbers modulo 3, but in terms of density, roughly half of the primes will give you some non-trivial congruence relations for the Fishburn numbers. numbers. And there are also similar congruences modulo prime powers. And these are nowadays theorems, so there are proofs why this works, but the proofs are, again, well, by number theorists who use their number theoretic arguments, and they do not really relate much to the combinatorial interpretation of those numbers, or any of the many combinatorial interpretations. So I'll mention as an open problem, can you find any combinatorial interpretation for these congruences? For instance, if you know that some Fishburn numbers are multiples of 5, well, that tells you that the corresponding interval orders of the given size n can be partitioned into 5 parts, which are all of the same size, but can you find some combinatorially meaningful such partition into 5 parts? So far, nobody can. Anyway, now I'll move forward towards the connection between Fishburn numbers and Catalan numbers. You are familiar with Catalan numbers? So Catalan numbers are a notorious counting sequence in combinatorics. They count the number of possibilities to nest n pairs of parentheses. They count plain binary trees or general plain trees and a few hundred other combinatorial objects, some of which I will show you in a moment. But I will begin by pointing out that Fishburn numbers really do not seem to be very closely related to Catalan numbers. So for Catalan numbers, there's an explicit formula. For Fishburn numbers, as far as anyone can tell, there really isn't anything of the sort. Asymptotically, Catalan numbers grow roughly like 4 to the n times some, or divided by some polynomial factor. Fishburn numbers are much larger. They grow like a factorial times exponential terms. And both these number sequences have some combinatorial interpretations. They count some objects. For Catalan numbers, there is now a catalog of several hundred combinatorial objects counted by Catalan numbers. For Fishburn numbers, there is also a handful. The generating functions, well, both counting sequences admit of sorts an explicit formula for the generating function. For the Catalan numbers, it's, I should say, more explicit than this summation of products, but okay. And algebraically speaking, the generating function of Catalan numbers is an algebraic function, meaning it satisfies an equation with polynomial coefficients. So these are quite a nice family of functions. On the other hand, the generating function for Fishburn numbers does not really fit into any such nice family. It certainly isn't algebraic. It's not even d-finite. If you don't know what d-finite means, don't worry. That's just a class of functions which are at least slightly nice. And Catalan Fishburn numbers have a generating function which is simply ugly by any standard you want to apply to it. And also from the analytic point of view, now I'm talking about generating functions here, but are they really functions? This is certainly a function. It's, I mean, if you express it as a summation of a power series where the coefficients are Catalan numbers, which is how generating functions are defined, you will notice that your series converges for some radius 1/4. On the other hand, if you express a power series whose coefficient of degree n is the Fishburn number, you will notice that it doesn't really converge anywhere except a single point. So this sum here really only is a convergent sum when x is equal to 0, when it all collapses and is equal to 1. So I'm talking about a function, but it isn't really a function in any meaningful sense. It's a purely formal power series. Right, so at first glance, these numbers do not seem like having too much in common, but I'll try to convince you that in fact there is a relationship. But to explain the relationship, I will need some time. Now, talking about Catalan numbers, I will fix one particular type of objects which are counted by Catalan numbers, and those are the so-called Dyck path. A Dyck path is what you see here on the picture, a path which starts in the point 0, 0, let's suppose it's here, and goes all the way to the point 2n, 0, and it stays in the non-negative half plane, so it stays above this dotted line, possibly touching it, and it makes two types of steps. It makes up steps where it goes up, and it makes down steps where it goes down. So some sequence of up steps and down steps which starts in 0, 0 and ends in 2n, 0 is a Dyck path, and it stays above the axis. And Dyck paths are known to be counted by Catalan numbers, and I will be interested in statistics on Dyck path. And the first statistic is the so-called number of returns of a Dyck path, which is simply the number of points where the path drops and touches the horizontal axis. So this path here has 2 returns. And the second statistic that I'll be interested in is the so-called tail, which is the number of down steps before the last return. So the number of down steps, so to say the length of the longest suffix made of down steps. That's the tail of a Dyck path. And I mean, maybe you don't like Dyck paths, maybe you like other Catalan enumerated objects. The point is that for most, at least for the best known Catalan objects, this statistics, return and tail, will translate into some notable statistic on your objects. So for instance, if instead of Dyck path you prefer plane trees, then there is a bijection between Dyck path and plane trees where the number of returns will correspond to the degree of the root of the tree, and the tail of the path will correspond to the depth of the rightmost leaf. So it's not really important that I'm choosing to work with Dyck path. Whatever, for most other Catalan objects, you could also define these some analogous statistics here. And the interesting feature of these statistics is that on the set of Dyck paths of a given length, they have what people call symmetric joint distribution, which is to say that the number of Dyck paths of a given length that have k returns and tail of length L is the same as the number of Dyck paths that have L returns and tail of length k for any k and L and fixed length of path. So there is this symmetry property of statistics on Catalan objects. And what I want to do is now to translate this symmetry property into the language of Fishburn matrices, which is possible because in this large class of interval orders, there are at least 2 notable subclasses which are enumerated by Catalan numbers. Specifically, the interval orders that additionally avoid this posets 3 + 1 are counted by Catalan numbers, and the interval orders which additionally avoid this poset that I call n are also counted by Catalan numbers. So I can do what I can do with any Catalan enumerated family. I can pick the family and try to find some pair of statistics which will have this Kreveras symmetry property. And I don't really like to work with posets, so I first translate this terminology into matrices, Fishburn matrices in particular. So here's some more terminology. Say I have a Fishburn matrix like this, and a north-east pair or NE pair is a pair of non-zero cells which which have this northeast neutral position. So the second cell in the pair is strictly to the right and strictly above the first one. Any such pair of non-zero cells in my matrix will be called an NE pair or northeast pair. And a southeast pair is very similar, but with one little twist. So a southeast pair of cells in a matrix is again a pair of non-zero cells that have mutually this southeast position. So the second one is strictly to the right and strictly below the first one, but, and there's an important extra condition which is expressed in this inequality here, but geometrically speaking, I insist that in a southeast pair, the sort of bounding box of the two cells must be completely on or above the decreasing diagonal. So for instance, taking this cell with 1 in the middle and this cell number 2 down here will not form a southeast pair because their bounding box drops below the diagonal. Does it make sense? So in this matrix here in particular, there are two possible southeast pairs. There are two southeast pairs, this 1 together with this 4, and this 1 together with 3, and no other. And I will say that a matrix is NE free or SE free if it has no NE pair or SE pair respectively. And when you take this translation between matrices and interval orders, it turns out that these two Catalan families correspond to the two families of matrices which I have just defined. Let's just check the definition. So the 2 + 2 and N-free posets correspond to the SE-free matrices, and the 2 + 2 and 3 + 1 free posets correspond to NE-free matrices. Okay, so far what I did was I found, or I showed you two more families of objects which are counted by Catalan numbers to add to this several hundred already known. And now I would like to define some analog of returns and tails that would have this nice symmetry properties on this SE-free and NE-free matrices. And that, of course, calls for still more definitions. And here comes an NE extreme, or a northeast extreme, is a cell in a matrix such that all the other cells which are weakly above and weakly to the right are zeros. Best seen on this picture, where this matrix has 3 northeast extremes. And southeast extremes can be defined similarly, but maybe an equivalent and more direct way to define what a southeast extreme is. It's a cell which is on the main, in this case, decreasing diagonal. It is non-zero, and there is no other cell in the same row. So this matrix here has 2 such southeast extremes. And I'll be looking at three statistics on Fishburn matrices, namely the number of northeast extremes, the number of southeast extremes, and the weight of the last column. So in this matrix here, well, this is the same matrix here, I have 3 northeast extremes to southeast extremes, and the weight of the last column is 5, 3 plus 2. So among those three statistics, the first two are really counting the number of non-zero cells with some property, and they do not care about the actual value of the cell as long as it's non-zero. But the final statistic is actually caring about the value of the cells. It's really the total weight of the last column. And it turns out that now I can take a bijection from Dyck path to matrices. I will in fact show you the bijections, and it turns out that when you biject from Dyck path to southeast free Fishburn matrices, then returns and tails will translate into northeast extremes and last column weight. And similarly, if you biject from Dyck path to northeast free Fishburn matrices, then the returns and tails will biject or translate into southeast extremes and last column weight. Let me give you the picture. So how do I translate from a Dyck path to a 2 plus 2 and n-free poset, and from there I can easily go to SE-free matrices. So I've been given a Dyck path. First thing I do is I define the so-called tunnels in a Dyck path. That's a standard terminology, and a tunnel is those are the red segments that you see here. Every tunnel connects the midpoint of an upstep with the midpoint of the opposing downstep, as in this picture. And now I can take those tunnels and project them to the horizontal axis, and that gives me a family of intervals, like so. So now I have from a Dyck path of order n, I have a collection of n intervals. And from a collection of n intervals, I can build an interval order, and from an interval order, I can build the corresponding matrix. And it turns out that this is a bijection all the way through. And well, if I look at the returns will map to northeast extreme cells, and if I look at the tails, which will map to the actual maximal elements in the poset, which corresponds to the weight of the last column. It does what I advertised, and therefore I can have this theorem which says that on the class of southeast free Fishburn matrices, the statistic number of northeast cell and the weight of the last column has symmetric choke distribution. Why not? And it works actually quite similarly for this 2 plus 2 and 3 plus 1 free posets and northeast free matrices. The only difference really is that instead of tunnels, I now define what some people call bounces. So I start in the middle of an upstep, I go diagonally down, I bounce off the x-axis and go up, and I end up in the middle of a downstep. So for every Dyck path, I can build a collection of this hook-shaped bounces. And again, projecting them downwards to the x-axis, I have a collection of intervals. From a collection of intervals, I have an interval order, which ends up being 3 plus 1 free. And from that, I have a matrix, and the statistics do what I promised they would do. So the number of returns here is the number of SE extremes here, and the tail of the path will be the weight of the last column. So again, I have some joint distribution of some statistics on some strange matrices. But all this is not really any novelty. It's just taking the old Krevera's symmetry property on Dyck path and following through the bijections, seeing what it tells me about my Catalan enumerated objects. And you can, if you are so inclined, do this with basically any family of Catalan enumerated objects. But the point, before I go to the point, which I will draw this symbolic picture. So I have this class of all Fishburn matrices, and inside the class there are two notable subclasses of northeast free matrices and southeast free matrices, both enumerated by Catalan numbers. So I should warn you that this picture is not made to scale. In reality, the class of Fishburn matrices is huge compared to the Catalan enumerated classes. But I know that on these two tiny little subclasses, there are some equidistribution results about statistics. And the punchline of this whole talk about Catalan object is that this symmetry of statistics that I have on these two Catalan subclasses is works also if I look at the whole class of Fishburn matrices. So these three statistics make sense for an arbitrary Fishburn matrix, and it turns out that any two of these statistics have a symmetric joint distribution on the class of all Fishburn matrices. That's not obvious. It certainly does not follow in any direct way that I can see from this playing with Catalan objects, but it is true. Some of it is proven by direct bijections. Some of it we can only prove by looking at generating functions and observing that they have some, well, they are symmetric in some variables, but this is what it is, and we don't really know, or at least I don't really know how or why, or any such deeper understanding of why this symmetry property of Catalan objects is reflected in analogous symmetry property of the Fishburn objects. Ideally, one would like to see some sort of theory which says that the Catalan world and the Fishburn world are somehow connected with each other and have this symmetries which translate, but so far there is nothing similar to such a theory. So this is, for all we know, just some kind of a cute coincidence. Okay, thank you for your attention.
Questions?
So, like, you showed that the joint distribution is symmetric for the special subclasses.
Yes.
And it's also symmetric for the whole huge class.
Yes.
Are these distributions somehow similar? Like, can you say that these small subclasses are kind of central to the huge class, or?
Not as far as I can say. I mean, I don't see any similarity in the numbers themselves. So, I mean, I have a like tiny number of Catalan objects which have some distribution, and then it's like a little drop in a huge ocean of Fishburn objects which also have some statistics and their distribution, but I don't see any like connection between the statistics.
If I pick some n, like 1000 is a good n, like good size of an object, then like would like the expected number of like what is it, southeast pairs be the same for a general Fishburn matrix as for a specific Fishburn matrix or something like that?
So
that's the question.
The averages or something like that. I mean, first of all, it's quite tricky to say what a random Fishburn object of a given non-trivial size will look like, although there are actually quite recent results which give some kind of asymptotic normality for some statistics, but I believe not for for the statistics that well, certainly not for the. Actually, there might be some results which give you some asymptotic behavior of the statistics, but they are not really impressive in the sense that they say, okay, this is normally distributed, and if you have one statistic which is normally distributed and another which is normally distributed, that's not all that big deal because lots of statistics are asymptotically normally distributed. So I really don't have any positive answer to this question. I don't know if there is any statistical connection between these Fishburn and Catalan statistics.
So maybe in a different way. So it's a symmetric joint distribution is the only thing we know about these distributions. Nothing like the expected value of the distribution. We don't know anything else about this.
I'm pretty sure people know a lot about the Catalan statistics, which are very well known, and I'm sure somebody has taken the trouble to count the averages or asymptotic behaviors there. I don't know what I don't even know what's like the behavior there, and I don't think we know much about the Fishburn statistics. I mean, for the Catalan statistics, there's like an explicit formula of how many Dyck paths of the given number of tails, given length of tail there are, and it's not all that difficult a formula either. It's, one could say, an exercise, but for the Fishburn.
Some more questions? Okay. If not, then let's thank the speaker again.